Okay, guys, it's Mr. Caldwell looking to go over the intermolecular forces sheet. And so let me share that screen with you. Hope everybody is doing well. And let's go ahead and make sure that I've got what I need on. Here we go. Here we go. And I think we're in. Sorry about that. Sometimes the technology likes to give me a little bit of a hard time. Okay, so here we are. And what I want to do is just kind of walk everybody through what's going on with these intermolecular forces, because they can be really tricky for students, all right? And so we'll start off by looking at comparison of methane, molar mass of 16 grams to water, 18 grams. We're going to draw a quick Lewis dot structure. So we've got CH4, and we know carbon has 4 valence electrons, 4 hydrogens. That brings a total of 8 to the picture, and I've got 8 drawn. H2O, at this point, we should know the drawing for this, and I'll go ahead and give it its bent shape because it's got 2 bonded atoms and 2 lone pairs. So then we go back and we think about, is this polar or non-polar? Well, it's, even if there are polar bonds, it is symmetrical, so it's going to be a non-polar molecule. And then this guy, because it's bent, it's going to be asymmetrical. You got these lone pairs hanging out up here, so you've got a really negative part of the molecule and a really positive part of the molecule. So this is definitely polar. And something to keep in mind here is that you've got hydrogens attached to oxygens. And when we looked at the video from yesterday, excuse me, hydrogens attached to either fluorine, oxygen, or nitrogen is a pretty strong composition of intermolecular force. So let's run through the types of intermolecular force that we have. Because it's nonpolar, the only thing that we're going to worry about are London dispersion forces, also known as van der Waals forces. And so London dispersion forces, remember, those are the weakest of the intermolecular forces. Polar molecules, well, let's see here. Even though, excuse me, even though it is a polar molecule, there are still electrons. So there are going to be LDFs. But more importantly, because it's polar, you're going to have dipole-dipole forces. And then on top of that, you've really got to remember that there is hydrogen bonding going on. So when we compare these and we look at the fact that the methane is a gas at room temperature, which means it has a very low melting point and boiling point, and water is a liquid at room temperature, has a relatively higher melting and boiling point. The reason for the difference is simple. CH4 only has LDFs, and those LDFs are weak. So CH4 does not hold on to its neighbors very tightly, hence the low melting and low boiling points. And then H2O has all 3, and primarily the really strong one is the most important, the H bond, the hydrogen bonding. Those are super strong, and so the water molecules hold on to their neighbors very tightly, giving it a much higher melting point or boiling point. So that's number 1. All right, let's go in here and look at number 2. So we've got HCl and HF. Now, both of these are very similar in terms of their structure. We've got H bound up with Cl, and then we've got H bound up with F. Sorry for the shaking there. And in terms of molar mass, 20 to 36, yeah, they're different. But you look at this, and HCl, let's think about what it has, all right? It is going to definitely be polar. The electron's going to be drawn more towards the chlorine than the hydrogen. So in terms of intermolecular forces for the HCl, yes, it has electrons, so it has LDFs, London dispersion forces. It is polar, so it's going to have dipole-dipole. Now here's where you have to be careful. Even though there is a hydrogen there, it is not bonded to either fluorine, oxygen, or nitrogen. So you've got to not say hydrogen bonding. It's tempting. You're like, oh, there's a hydrogen there. It's not hydrogen bonding. It's not bonded to either fluorine, oxygen, or nitrogen. All right, and then you come over here to HF. HF is going to have a very polar molecule because fluorine is one of the most electronegative elements that we have. In fact, is the most electronegative element on the periodic table. So the electrons are drawn very much towards the fluorine, leaving this side very positive, this side very negative. And so in terms of intermolecular forces, you've got London dispersion forces. You've got, and I'm just going to abbreviate, dipole, and this one is hydrogen bonding because it is bonded to one of our big three, fluorine, oxygen, or nitrogen, the three biggest electronegativity elements on the periodic table. So why does HF have a boiling point of 19.5, which is much, much higher than the boiling point of HCl? Comes down to the fact that HF has got hydrogen bonding, and get rid of that, and HCl only has dipole. HCl only has dip, whereas HF goes all the way up to H bonding. So HF is going to hold on to its neighbors much more tightly than HCl holds on to its neighboring HCl molecules because of the presence of all three, London dispersion, dipole, and hydrogen bonding for the HF. Okay, and let's continue. Number 3. All right, let's look at this and draw again. The Lewis dot structures are the key. And so we go in, we got CH4, which we already drew, and which we already know is going to be non-polar. And so we already know that it is going to be just LDF. CH3Br, all right, CH, H, and then we throw a Br on here. And I can tell you from having done this a while, the electron count is all good. Now, we're going to have LDFs because there are electrons. Is this going to be polar? Yeah, it is actually, because this is going to be a polar bond, and it is definitely asymmetrical. So we're going to end up with a polar bond. So not only do we have London dispersion forces, we also have dipole. And so at that point, we know that CH3Br is going to hold on to its neighbors more tightly than CH4 would hold on to its neighbors. So CH3Br should have the higher boiling point, which means methane has the lower boiling point. So the reason is CH4 only has LDFs, CH3Br has LDFs, and dipole. So hopefully going over these is good for you guys and is making some sense of this relatively tricky topic. All right, last but not least. Okay, so ecosane, all right, has got an awful lot of carbons and hydrogens. Now, I don't really want to draw all of these, so I'll just draw a couple of them, and I'll put some dots and a couple of them, and we're going to draw lines, and at the end of each of those lines is an H, okay? There's a tremendous number of carbons and hydrogens here. Now, I guess I could draw all 8 if I had to. 1, 2, 3, 4, 5, 6, and then, oh goodness, let's put all those hydrogens on there. I'm not going to draw the H's. All right, but at the end of the day, here's the thing. These guys, both of them non-polar. So you are comparing a non-polar to a non-polar because they're all symmetrical. So the only thing at play, both of them have London dispersion forces. So who kind of wins? Who has the stronger intermolecular force? You go with the one that has the largest molar mass because this one is going to have way more electrons, which could create a way larger temporary dipole. If all those electrons hung out in this spot right here for just a brief moment, this would create a very large area of negativity and a large area of positivity. This one would be smaller. And so that is going to drive what is happening here. This guy is a solid at room temperature because it has a higher melting point, higher boiling point than octane. because octane has fewer electrons, thus a weaker London dispersion forces than the icosane. So the molar mass of C20H42 is greater than the molar mass of C8H18. Both have only LDFs. And that is it. So hopefully that was a nice little kind of run through of those 4 problems for you. And hope to see you online again soon. You guys be well. Take care. All right. Bye-bye.